Hello everyone, I'm Shixiong Zhao from the University of Hong Kong, supervised by Pekhimenko. We will present NASPipe, a high-performance and reproducible pipeline parallel supernet training system via causal synchronous parallelism. This work is collaborated with Huawei and the University of Science and Technology of China. Nowadays, deep neural networks are needed on various devices with different hardware and accuracy requirements. And neural architecture search is a great technique to automatically design deep neural networks meeting these complicated deployment constraints. In particular, Supernet is an extremely significant NAS paradigm because it provides great efficiency. A Supernet is constructed by composing all possible DNN operators. A company like Huawei only needs to train a large network only once, and then they can extract subnets from the large Supernet to deploy on different devices. Here is an example of a supernet. It has 3 possible DNN operators in each layer, and the resultant subnet for certain constraints is to choose a small number of operators from each subnet layer. For example, the yellow color operators are a subnet optimized for watch, and the blue color operators are another subnet optimized for phone. The 2 subnets can be directly searched from a parameterized supernet without training. An important question here is how a supernet is actually parameterized. To parameterize a supernet with high accuracy, the existing supernet is trained in a traversal way. During the training process, a supernet traversal algorithm iteratively activates and then deactivates one supernet in each training step. And each subnet takes one training input batch. The benefits of doing so are noteworthy. On the one hand, at any time of training, actually there is only one supernet being activated. This greatly saved the GPU memory for storing training intermediate results, and more importantly, such a traversal way has been shown to have a high supernet training accuracy. For other supernet training methods, they often let supernets concurrently perform parameter updates on the shared supernet operators, and this makes the good subnet accuracy interfered by bad subnet. Notable accuracy losses caused by such interference have been observed both in our evaluation and related studies. While the one-by-one supernet traversal is effective, recently we have seen that the deep neural networks are getting larger and larger. And the design space of DNNs is also spanning quickly. Therefore, a one-by-one supernet traversal is requiring much more time and GPU memory. This brings the need to accelerate the traversal of supernet in parallel with more GPUs. However, existing distributed training systems are mainly designed for monolithic DNN training, and they are not designed to train multiple subnets of supernet that switches in the second level. The particular challenge here is that in supernet training, subnets may have shared operators. So naively parallelizing the one-by-one traversal can introduce non-deterministic interference between subnets. And in this paper, we built NASPipe, a system that targets at training multiple frequently activated and deactivated subnets in parallel and deterministically resolving the potential interference caused by operator sharing. Why do we need deterministic interference resolution? The reason is that deterministic training is an extremely desirable feature pursued by most existing machine learning frameworks and the research communities. For example, both PyTorch and TensorFlow has the deterministic training feature at the DNN operator level. And for supernet training, researchers often need to rerun or reproduce a supernet to debug and analyze an algorithm. In short, existing works achieve determinism at different levels, including the DNN operator level and the supernet traversal algorithm level. Therefore, given a set of good random seeds and a good supernet traversal algorithm can always produce the same traversal order of subnets. With the one-by-one execution of the subnets, we can always get a highly accurate supernet. Instead, NASPipe pursues the determinism at the parallel NAS supernet training level. We believe that NASPipe is complementary to these works. NASPipe is built as a pipeline parallel training system, and why we choose so. Pipeline parallel training is a parallelism paradigm that is suitable to train extremely large DNNs, and we believe pipeline parallel training is a desirable match for Supernet NAS training for a few reasons. First of all, pipeline parallel training partitions the Supernet into multiple GPUs, and this can help support large Supernets. And in each training step, an activated subnet processes one input training batch with a forward pass and a backward pass. With pipeline parallel training, NASPipe executes multiple subnets that carries multiple input batches in parallel and forms a pipeline. The processing of each training input batch is to read a subnet's parameter in the forward pass and produces some intermediate results that is passed between connected pipeline partitions. In the same subnet's backward pass, it will read again the subnet's parameter and the previously produced intermediate results, and then produce and write the parameter updates to the subnet's operators. The question is, when subnets may have shared operators, what would happen if we simply pipeline multiple subnets in parallel? The answer is that when we parallelize the Supernet training with existing pipeline parallel training systems, interference problems caused by the operator sharing happens again. Specifically, even we feed the subnets in a total order into existing pipeline parallel training systems, the subnet's read and write dependency orders on the shared operators can be still non-deterministically scheduled. For example, the left table shows 7 subnets, and some subnets have dependencies on shared operators. The marked box means the higher ordered subnet 2 has shared operators on a lower ordered subnet 1 on Supernet partition 0. When we execute the subnets in a pipeline manner, either with an asynchronous parallel scheduling or backsynchronous parallel scheduling, both parallelisms may violate the total orders on accessing the shared operators. In the right figure, arrows means in a correctly ordered training, a higher order subnet's forward pass should read the shared operators after written by a lower ordered subnet's backward pass. The green arrows means such dependencies are followed, while the red arrows means such dependencies are violated. Note that the left table is actually maintained by NASPipe, and no existing systems are aware of these dependencies. For more details about the interference problem, please refer to our paper. Now we conclude the interference problems in pipeline parallel Supernet training more briefly. For multiple totally ordered subnets having shared operators, when we execute them in a pipeline manner, even we feed them into the pipeline according to their total order, their concurrent read and write on shared operators can still non-deterministically cause data races. This not only breaks the desirable deterministic training feature, but also empirically lowers the Supernet training accuracy. For example, suppose the subnet 2 has good quality, but its quality can be easily hindered by subnet 1, because subnet 2 should compute on subnet 1's updates, but it actually never sees the subnet 1's updates. In NASPipe, we present a new synchronization model called Causal Synchronous Parallelism. In CSP, for subnets accessing shared operators, we carefully synchronize their accesses to the shared operators to obey the total order. For subnets without shared operator dependencies, we can execute them firmly in parallel. Consequently, as long as the total order of subnets is the same, and the causal dependency between subnets are solved deterministically, and the Supernet training quality is the same between different rounds. Here is an example of how NASPipe enforces causal synchronous parallelism with high efficiency. The left is still the dependency table, and the right is the new CSP scheduling produced by NASPipe. The scheduling enforces all the dependencies between subnets with the green arrows in the figure. Remember that the green arrows mean the higher ordered subnet's forward pass read correctly sees the lower order subnet's backward pass write on the shared operators. And now we focus on how the scheduling works on the first GPU, which is the partition 0 of the supernet. First, we executed subnet 1 forward pass, and next, we want another subnet forward pass to form a pipeline. However, we look at the dependency table and found that subnet 2 should wait for subnet 1's backward pass. So we schedule subnet 3 next. And we can also freely put subnet 4, 5, and 6 into its scheduling because these subnets also have no dependencies with the lower order subnets on partition 0. In the next period, we can see that the backward passes of subnet 1 are always scheduled with the highest priority because always executing backward passes first helps remove the dependencies. Doing so greatly improves NASPipe's parallel efficiency. After subnet 1's backward pass finishes on partition 0, we have the subnet 2's dependency on the subnet 1 removed, and then we can schedule the subnet 2 into execution. So actually, on each GPU, we schedule the subnets locally because we only need to check the subnet dependencies on the local partition. This makes NASPipe's training scheduling algorithm actually a decentralized and scalable algorithm, since every GPU maintains the causal dependencies on its own without performance bottleneck of a centralized master node. Here is the per GPU system architecture of NASPipe. On each GPU, NASPipe actually has a scheduler that enforces our highly efficient CSP scheduling. And we also have a predictor. Remember that in Supernet training, actually only one subnet is activated at any time. Therefore, NASPipe takes the GPU memory as the main storage, and switches subnets into GPU memory before they are actually executed. NASPipe predictor is a one-step more forecasting of our CSP scheduling, so that we can precisely prefetch the subnets into GPU. This releases more GPU memory for computation and greatly improves NASPipe's training efficiency. You can read our paper for more details. Here are more implementation briefs of NASPipe. NASPipe is implemented on PyTorch, and NASPipe's design is extensible to any imperative deep learning frameworks. NASPipe adopted activation checkpointing for saving training memory, and we enabled all deterministic options in PyTorch. We also designed the CUDA stream management for asynchronous context switch and network I/O. And finally, NASPipe has an operator mirroring mechanism to balance execution at runtime between pipeline partitions. Our evaluation compared NASPipe with three notable pipeline parallel training systems: JPipe, PipeDream, and VPipe. Here is the GPU farm setting of our dedicated cluster. The evaluation part focuses on two of our evaluation questions. The first is NASPipe's end-to-end performance comparison with the baselines, and the second is the evaluation that shows NASPipe's reproducibility on Supernet training. For the end-to-end performance, Figure 1 shows that NASPipe achieved 1.5 times to 7.8 times speed up over the baselines. Specifically, with larger search spaces, NASPipe speed up over baseline systems get larger. Table 1 shows why NASPipe can achieve a higher training throughput compared with baseline systems. The main reason is that NASPipe uses the GPU memory as the main storage, and it can precisely prefetch the subnets into GPU memory with a high cache hit rate. This greatly improves the effective GPU memory utilization because it saves the memory for storing the sparsely activated Supernet parameters. This leaves more GPU memory for NASPipe to support a larger batch size, with a negligible non-context switch overhead. Larger batch size make NASPipe achieve a higher GPU ALU utilization. For the reproducibility of NASPipe, firstly in Table 3, we can see that given the same initial random seeds across settings of different number of GPUs, only NASPipe with CSP can exactly reproduce the same Supernet training loss and the same resultant search accuracy. In Table 4, we further break down the accessed orders of an operator. NASPipe is the only system that deterministically preserves subnet access orders on the shared operators. For BSP and ASP, the orders cannot be reproduced. We also observe that NASPipe achieves the highest supernet training accuracy, and meanwhile, a lower supernet training accuracy can be observed with BSP and ASP. Overall, as long as fixed random seeds are given, NASPipe always produces the same supernet training procedure across different executions with different number of GPUs in the pipeline. Meanwhile, all over the training procedure, NASPipe has achieved the highest effective GPU utilization. In this paper, we present NASPipe, the first high-performance, reproducible, and accurate supernet training system via causal synchronous parallelism. Our newly proposed synchronization model CSP meets the need of efficient parallelism and interference avoidance. NASPipe can not only help the development of better supernet traversal algorithms, but also help to design better supernet debugging and analysis tools. NASPipe can serve as a distributed backend of existing supernet programming frameworks, such as Theory. And we believe NASPipe has extension potentials to more sparsely activated DNN paradigms, such as mixture of expert models, dynamic routing models, and multimodal DNNs. Of course, supporting these cutting-edge DNN paradigms in NASPipe requires solving new research challenges, and we leave it for future work. NASPipe's artifact is available on GitHub, and that's all for our talk. And thank you for listening.